for us given xi and xi minus 1 or how to go on to find xi plus 1, and I have summarized this in the table. So the 5 methods that we looked at: bisection, regular falsy. Regular falsy is also known as method of false position, fixed point iteration, which is also known as successive iteration or successive substitution method, then the secant method, and then finally the Newton-Raphson's method. The bisection method starts with 2 initial guesses. Reguli falsi also starts with 2 initial guesses. These 2 methods are bracketing methods. Because they are bracketing methods, the 2 initial guesses have to lie on either side of the solution. When it comes to a fixed point iteration, when it comes to a secant, when it comes to fixed point iteration, and when it comes to Newton-Raphson's method, we only need 1 initial guess, whereas in secant method we need 2 initial guesses. Strictly speaking, in secant method we do not need the 2 initial guesses to fall on either side of the solution. We can start with 2 arbitrarily chosen initial guesses also. Okay. And xi plus 1, this is how we move from the current guess to the new guess xi plus 1, and bisection is nothing but midpoint of the 2 solutions xl and xr. In case of a regular falsy and in case of secant method, we join the line connecting the point x comma f at xl and x comma f at xr, and find where that straight line intersects the x axis. As a result of this, both these 2 expressions, both these 2 methods have the same expression. The only difference in regular falsy is we retain the solution such that one solution is to the left hand side of the true solution, then the other solution is to the right hand side of the true solution, whereas in secant method we only keep the solution, the ith solution and the I minus 1 solution, only the latest 2 solutions. Okay. The fixed point iteration, we use xi plus 1 equal to g of xi, and in Newton-Raphson's method xi plus 1 is xi minus f divided by f dash computed at xi. We also looked at the order of convergence, we also looked at the order of convergence. Bisection method was first order convergence, fixed point iteration also was first order convergence, first order method, and Newton-Raphson's method we saw was the second order, has a second order, a quadratic rate of convergence. We did not derive the rate of convergence for regular falsy or for secant method. Regular falsy and secant method have a superlinear rate of convergence. That means in the expression ei plus 1 equal to ei to the power eta, eta is a value that lies between 1 and 2. Typically it lies very close to the golden section rules, golden section. In general, you can expect in the regular falsy method to the order of convergence to be anywhere between say 1.4 to about 1.6. That is what the regular falsy ends up being. For secant it is equal to the golden section. Okay. Then stability, given the 2 initial guesses are feasible initial guesses, the bracketing methods are guaranteed to be stable, whereas the open methods, as we have seen, there is no guarantees on stability of the open methods. In fixed point iteration method we looked at a numerical example where the fixed point iteration does not converge. Although we did not look at numerical examples for secant and Newton's that does not converge, we really motivated these 2 examples using some kind of a graphical method to say under what conditions these methods are not going to converge. Now the issues, the important issues with respect to all of these methods is that bisection and regular falsy are essentially single variable methods, and we have to ensure that f of x changes the sign at x bar. So for example, an equation of the sort f of x equal to x square, you cannot use bisection method because we will not be able to find xl and xr which satisfy f of xl multiplied by f of xr equal to less than 0. That is because if f of x is equal to x square, the f of x is always going to be positive no matter what value of f of x we use. Okay. The fixed point iteration, the applicability is limited because of stability issues. We saw that this conditions for stability of fixed point iteration were fairly stringent conditions for stability. The secant method and the Newton-Raphson's method are both very versatile and very fast methods, specifically the Newton-Raphson's method. It is a very versatile method. And the reason for popularity of Newton-Raphson's method is, one, because it is extendable to multivariable systems. Second, because when f dash of x is not available, we can actually use a numerical derivative, and when we use a numerical derivative, the Newton-Raphson's method kind of resembles a modified secant method in some ways. And the overall requirement is that the Newton-Raphson's method should not have f dash of x equal to 0. If f dash of x equal to 0, then the Newton-Raphson's method cannot continue. So a requirement for Newton-Raphson's method to continue is that f prime should be not equal to 0. And likewise, we should start with an initial guess which is not far away from the 2 solution x bar, and it is applicable to multivariable system, and that is the reason why Newton-Raphson's is what we considered for multivariable system, as well as we considered the fixed point iteration for multivariable system. So the extension to multivariable system for fixed point iteration we saw was straightforward. It kind of follows the same idea that we used in the Jacobi iteration. So when we have the equations x bar f of x bar equal to 0, all we need to do is essentially x of I plus 1 should be equal to, there is a typographical error over here, this should actually be g and not f. So x to keep up with really the previous notations. So x of I plus 1 should be equal to g bar of xi, and this is what we need to iterate on over and over again in order to get until we converge when we are going to use fixed point iteration. We saw that the sufficient condition for convergence is that the absolute values of the sum of the absolute values of partial derivatives of the function with respect to x1, x2 and so on up to xn should be less than or equal to 1. Okay, this is the condition for convergence, and I had stated without actually proving or without actually looking at the examples that this often ends up being a fairly stringent condition for fixed point iteration, which limits actually the applicability of the fixed point iteration method. Okay, and then we looked at the multivariable Newton-Raphson's method, and the multivariable Newton-Raphson's method is xi plus 1 is xi minus j inverse f, where j is nothing but Jacobian, and this is how the Jacobian is written, df1 by dx1, df1 by dx2 and so on up to df1 by dxn, and on the column we have df1 by dx1, df2 by dx1 and so on up to dfn by dxn. So we essentially get this square matrix. These values have to be computed at the guess x bar at I, and we substitute that over here, we multiply that with the function value computed at x of I, and this is the iterative equation that we will get. The Newton-Raphson's multivariable method also has a quadratic rate of convergence, and then what we looked at is certain improvements that have been developed to improve the speed of convergence or to improve the stability of the Newton-Raphson's method. Okay, so the Ralston's modification, and this is something that we considered in this lecture also, the Ralston's modification, if there are m roots, is that instead of having xi plus 1 equal to xi minus f divided by f dash, instead of that we multiply this with a factor m. Another improved Newton-Raphson's method based on the Ralston's modification we said was, if we write h of x equal to f divided by f prime, the roots of f of x are going to be the same as the roots of h of x. So all the roots of f of x will also appear as roots of h of x, and based on that we obtained a modified Newton-Raphson's formula, In fact, if we rigorously derive this particular formula, we will notice that this is a third order accurate formula. So, we can actually improve the accuracy of the Newton-Raphson's method from a second order accurate to a third order accurate method. The pitfall or on the flip side for this particular method is not only do we need to calculate f prime, we also need to calculate f double prime in order for this particular Newton-Raphson's the third order Newton-Raphson's method or the improved Newton-Raphson's method to work. Okay. The other modification, so these modifications were for multiple roots and especially to speed up the Newton-Raphson's method for multiple roots. More importantly are the modifications that ensure stability of the Newton-Raphson's method, and one of the biggest or two major problems that we had seen with Newton-Raphson's method is, one is when f prime of x becomes equal to 0, and the other case is when cyclically we keep repeating the same roots. So that means the root xi sends us to xi plus 1 and then xi plus 1 sends us back to xi. So xi plus 2 equal to xi equal to xi minus 2, xi minus 2 equal to xi minus 4, so on and so forth. So we will not get convergence, we will keep circling around the actual x bar. That is also a fairly common problem in Newton-Raphson's method. So a straightforward way of modifying the Newton-Raphson's method is what is known as a line search algorithm, and line search is very much like the Jacobi over relaxation or the Jacobi under relaxation that we had looked at. The only difference is instead of using a Jacobi type of an iteration, we use that under relaxation factor in the Newton's iteration. So instead of having xi plus 1 equal to xi minus j inverse f, we have xi minus omega j inverse f, where omega is a value between 0 and 1, and that is an under relaxation parameter. So what we are saying is we are going to take really smaller steps than what Newton-Raphson asks us to take, just to be a bit more conservative in tracking the solution. This will reduce the speed of approach to the solution. This is definitely going to reduce the speed of approach because of the under relaxation, but it will improve the stability of this solution. And there are various ways to get a good under relaxation parameter. These ways we are not covered in this particular lecture, and there would be suggested further readings if you are interested in knowing how to get this under relaxation factor. And then finally we also looked at a Leeuwenberg-Marquardt modification to the Newton-Raphson's method. Technically speaking, the LM method actually really comes in the optimization and finding out essentially a least square minimization. If you do not understand the terms, do not worry about it. The motivation behind this is that the roots of the function f of x are nothing but the minima of f square of x. We saw that essentially two lectures earlier what that means pictorially, and when we use this Leeuwenberg-Marquardt's modification, instead of having j inverse f, instead of that we will have j transpose j plus beta I, where beta is a very small factor inverse j transpose f. This is how to get the beta, and all that are fairly advanced techniques which you need to do further reading on in order to figure those things out. And in today's lecture what we looked at is the Bairstow's method for root finding. We actually did not go into the meat of the Bairstow's method because that would essentially involve a fair amount of basically it will involve fair amount of algebraic manipulations, which I think you will now be very well equipped to go and read up any of the textbooks to understand that. So that is why essentially for the lack of time we did not go into that, but the idea is that any nth order polynomial can be written as a product of n minus 2 order polynomial and a quadratic polynomial plus a remainder r. When the remainder r equals 0, at that time q is a factor of p. For example, in the examples that we had looked at, for example in this particular case, x square minus 1 is going to be a factor of this particular expression. So, if we choose the value of p equal to 0 and q equal to minus 1 and go through the procedure that we looked at in today's class, we will get C1 equal to 0 and C0 equal to 0. We are guaranteed to get that. That will tell us that x square minus 1 is essentially a factor of this, and it's because x square minus 1 is a factor of this, we will get x equal to 1 and x equal to minus 1 as the 2 solution, and the deflated polynomial p n minus 2 is going to be nothing but x minus 2. So, that will lead us essentially to the 3 solutions x equal to 1, x equal to minus 1 and x equal to 2. Okay. That was essentially about the Baire-Stokes method. What I urge you to do is just go and read up about the Baire-Stokes method in the second textbook that we have over here, Chapra and Canal numerical methods. So, this is where essentially we end our module 4, which was on algebraic equation solving. In module 5 we will talk about interpolation and curve fitting, or what is known more technically known as regression. That is what we will cover in the next module in this course. Thank you.